Hi, my name is Corinna Ulcigrai and I'm a reader in mathematics at the University of Bristol. And my research is in the mathematical theory of chaos. And I want to convince you today that chaos can be a good thing. And the objects that I studied in the past are mathematical billiards. So what is a mathematical billiard? Well, this is a kind of idealization of the billiard game, the one that you play in the pub. But it's a mathematical version of the billiard game. The table, in the classical case, it's a rectangle. In general, it could be some domain in the plane. And then you have a billiard ball. And the ball will be just a point with no mass. And you start by shooting your ball in a certain direction. So you know very well how the ball moves on the billiard table. So it moves along straight lines until it hits the boundary of the billiard table. And then it bounces off elastically. And the law is that it makes the same angle when it hits and when it comes out. So this angle of incidence and the angle of reflections are the same. And then you keep moving like this. So it keeps going on a straight line, and then it bounces off, making equal angles, and so on. And the differences within a mathematical billiard and a real billiard is that here there is no friction, so the ball will actually keep moving with the same speed forever, unless it hits a pocket, and the pocket could be the corners of this billiard table. But the main difference is with the real billiard that we don't want to shoot the ball in the pocket. But on the other hand, we really want to look at trajectories which will never enter a pocket and will keep moving forever. And we want to ask what will happen of the trajectory, what will be the behavior as time grows. So this is called the dynamical system. It's a system that moves in time. And sometimes it's actually very hard to predict what will be the long-term behavior. So even though, you see, the law is very simple and very clear, you know exactly what will happen next. You will hit and reflect according to this very deterministic rule. But on the other hand, sometimes the systems, like mathematical billiards, are quite complex and chaotic, so it's really hard to predict where exactly the point will be after many, many collisions with the boundary table. And so we try to just understand what is the global behavior and not the exact location of the point particle at every time. And for example, the first thing you can ask is, will your trajectory be periodic? So let me give you an example of a trajectory which is periodic. If I just shoot at a straight angle, the trajectory will bounce back, backtracking the same route, and will keep moving forever in this bouncing mode. So this is a very simple trajectory, periodic. Let me give you another example of a periodic trajectory. This one that I draw now, it's a periodic trajectory of order 4. So the ball here will bounce 4 times, and then exactly retrace the same steps over and over again. So this is a trajectory that flows up, and it's periodic. So could there be any more complicated behavior? This seems very special, and is very special. So if your trajectory does not close up, what will happen? Well, it turns out that actually in these simple rectangular billiards, there are really only 2 possible behaviors. So either you are periodic, like I just showed you, or at the complete opposite end, you will have a trajectory which visits or gets arbitrarily close to every possible part of your table. These trajectories are called dense. So there is a dichotomy, either a trajectory is periodic or a trajectory is dense. So why do we care? Why do we study mathematical billiards? So we don't study mathematical billiards because we want to play pool with friends at the pub. No, that's not the reason. The reason is that mathematical billiards appear naturally in many problems from physics and from the real world. So there are problems of acoustics, optics, and statistical mechanics and physics, which are modeled by a billiard. And let me give you an example. For example, there is a famous model of electrons moving in a metal, which is called the Lorentz gas, which is a billiard where there are holes, circular holes in the table, and the table is the whole plane without these holes. This you should think of as the atoms of a metal. They're put in a specially periodic way. And then your ball is actually an electron which bounces off the atoms in the metal. So a billiard system will describe, in this case, the motion of an electron in a crystal. And this is just an example. There are other models of gases which can be reduced to billiards. And there are also other physical systems, which is not so obvious at first, that can be represented by a billiard, but give rise to billiards in different shapes of tables. And let me say, in this case, this Lorentz gas, it has lots of symmetry. And if you reduce the symmetry and just look at one fundamental block, you get a very famous billiard known as Sinai billiard. And I really like to mention the Sinai billiard because Sinai was my PhD supervisor at Princeton University, and he was also the recipient of the Abel Prize this year. So let me draw the Sinai billiard. So it's actually a square billiard, but we put an obstacle in the middle, which is exactly a circle or some other convex scatter. So your billiard table now has a hole, so you cannot go in this central region. And the boundary of this obstacle are scatterers. So when your ball hits the scatterer, it bounces away with the usual angle of reflection. And the rest is the usual billiard table. Okay. Let me go on. So this billiard is much more complex and chaotic than just a rectangular or square billiard. And that's really because of the scatterer, this convex scatterer. So let's look at this picture. If you have trajectories which hit parallelly the scatterers, but at points which are just slightly different, the future evolution would be very different. And that's because of this scattering phenomenon. So parallel rates of trajectories open up and defocus, go in very different directions. And this defocusing mechanism, it's really at the heart of the chaotic features in these billiards. And this is what Sinai discovered in the 70s. So the fact that if you just make a small mistake, or if there is a small difference in the point where you hit, you will see a macroscopic, very large difference in what happens next. This is known, it's one of the examples of the butterfly effect. This is a very famous effect. And the idea is that it appears in many complex systems, for example, the weather. And the idea is that if you have a butterfly that flaps wings in some part of the world, this little difference in flapping could produce a huge deviation and produce a tornado or in some other part of the world. And in mathematical terms, this effect is called sensitive dependence on initial condition. So if you change the initial condition a little bit, you will see a huge variation in the future. And the Sinai billiard has a sensitive dependence on initial conditions. So it might seem that the situation is hopeless because the single trajectory is too complicated and too chaotic to be predicted. But on the other hand, even though you cannot understand the single trajectory, you can still understand the system as a whole. And if you can prove mathematically that the system is chaotic and has some mathematical features of chaos, then you know that on average you will still be able to make predictions on quantities that are of interest to you. For example, in the case of the gas, you might want to predict the average temperature or pressure or some other physical quantities. And in the case of the billiard, you might just want to know where a random trajectory will be. So for example, you can still prove that random trajectories will be filling up the whole space. And even you can measure how much time each trajectory will spend in different parts of your billiard table. And again, this is possible exactly when you can mathematically prove that your system has enough chaoticity, enough chaotic properties.